Hello, dear students of the third secondary grade, and welcome to a new episode of our program. On this episode, we're going to study a new lesson of physics. It's called the electromagnetic induction. This is chapter 11, and I have here in the studio with me Mr. Ahmed Abdulaziz, our teacher of physics. So let me first welcome him. Hello, Mr. Ahmed, and welcome to the program.
Hello again, and welcome again, you and our students, inshallah.
So, Mr. Ahmed, we're starting a new chapter, electromagnetic induction. So let us first know what is meant exactly by this title.
The title indicates a phenomenon which can be expressed as or defined as a phenomenon that is produced due to the cut of a coil or a conductor to the magnetic field lines formed from a magnet. But when the current induced, we must have electromotive force induced. So finally we can define this phenomenon as it is a phenomenon in which an induced electromotive force and induced current are produced due to the cut of a conductor or a coil to the magnetic field lines of a magnet. And we studied before in chapter 10 the magnetic effect on the electric current passing through the conductor, whatever, straight wire, loop, circular loop, solenoid. But this it is a verified coincidence. Firstly, Hans Ørsted was study an electric circuit, and he put a compass, a magnetic compass, beside the electric circuit. So the compass, when he closed the circuit, the compass needle deflected. So by coincidence, he discovered that when the current passing through a wire, there is a magnetic field is produced. But Faraday...
Yeah, I'd like to know how could Faraday verify this
Yes,
phenomenon?
Faraday, after a series of experiments, verified that the opposite of what Hans Ørsted explained. Faraday said that as we obtained from the electric current there is a magnetic field, we may obtain magnetic electric field from the magnet, the opposite of the idea of Hans Ørsted. And prove it or verify it as when you bring a coil and connect it to a sensitive galvanometer, the reading of pointer of 0 at middle of the pointer to determine the direction of current that is produced or induced inside the circuit. So we can explain it as it is drawn now. How Faraday verified the electromagnetic induction. Firstly, bring a coil connected to sensitive galvanometer, which reading 0 reading at the middle. After then, bring a magnet bar north and south, and he found that when it moves the magnet bar to be plunged inside the turn of the coil, the pointer will deflect in certain direction. But when it is removed, so it is the first step. Second step, what will happen? The pointer deflects in the other direction. or in the opposite direction. How and why? Because when the magnet moves toward the turns of the coil, there is a magnetic field produced due to the current or induce the current passing through the coil. So there is magnetic field produced as magnet power here in this side as north pole. So there is repulsion force, and the current will be as Ampere's right hand rule, this north and this south, so the direction this is filled. If we apply the Ampere's right hand rule, so the current will move in this direction. But when it removes the magnet away from the coil, by induction, this north pole will produce or indicate here a paramagnet where the negative pole changed into south pole, where the south pole changes into north pole. So it will be attraction force, and the direction of field be changed, so the direction of current will be changed. This very simple idea about the experiment of Faraday to indicate what the meaning of the electromagnetic induction.
All right, so this is how Faraday verified this phenomenon. Now I'd like to ask you about the ability. How can we calculate the induced electromotive force?
We can calculate it from the Faraday's law, because Faraday expected that. What is the factor on which the electromagnetic induction, which relates to the induced EMF and induced current produced, depends on? So Faraday expected that the rate time of magnetic flux that cut by the conductor, as it increases, the magnetic or electromagnetic induction will increase, and so the induced electromotive force and induced current will increase according to the relation. So it explained that EMF induced is directly proportional to the time rate of magnetic flux that cut by the conductor or the coil. And also it explained that the electromotive force or induced electromotive force is directly proportional to the number of turns if we talk about a coil. So from these two relations we can conclude finally EMF induced in a conductor equals negative N delta phi m divide delta t. What about this negative sign? This negative sign indicates Lenz's rule. What about Lenz's rule? It is defined as the induced current must be to oppose the changing causing it. The change causing it. So Lenz's rule is defined as the induced current must be to oppose the change causing it. So as we see before, when the magnet moved away from the turns, the magnetic field which produced in the coil changed. So the induced current will be changed in the direction also. Again, Lenz's rule is defined as what? The induced current must be to oppose the direction of change causing it. Finally, we can calculate EMF as we see now. Electromotive force induced equals negative, which related to Lenz's rule. Number of terms, delta phi m divide delta t, the time rate of magnetic flux that cut by the conductor or cut by the coil.
All right. Now I'd like to ask you about how we can determine the direction of the induced current.
Exactly, we use Fleming left-hand rule, as I make now. Make thumb, pointer, and rest of the left hand fingers to be mutual to each other or perpendicular to each other. And then, if the thumb directs to the motion of the coil or the straight wire, a conductor, whatever, and the pointer directs to the magnetic field, finally, the rest of fingers or the middle finger directs to or points to the direction of the induced current. So, before we left this point, we must determine that there is difference between Fleming left-hand rule and Fleming right-hand rule. Fleming right-hand rule used to indicate the direction or to determine the direction of the motion or the direction of magnetic force acting on a straight wire carrying current. And it is decided as if you make the fingers of right hand, thumb, pointer, rest of right hand fingers perpendicular to each other, and where the rest of fingers direct to the current, pointer directs to the magnetic field, therefore the thumb points to or directs to the magnetic force acting on the wire. But here, Fleming left-hand rule used to determine the direction of induced current, where we will start with the thumb. Here we start with the rest of fingers. So, magnetic or Fleming left-hand rule used to determine the direction of induced current, where if you make thumb, pointer, rest of fingers of the left hand or the middle of the left hand perpendicular to each other, where the thumb directs to the motion or the acting force, the pointer directs to the magnetic field, therefore the rest of the fingers of the left hand directs to the induced current. So we can determine or indicate the direction of induced current using Fleming left-hand rule. Yes.
All right, I guess it's time for us now to start applying these rules by having some examples.
Okay, it's up to you.
All right, let us start with the first one.
Yes.
Which says a rectangular coil of 30 turns and dimensions of 25 centimeters and 15 centimeters if it rotates with fixed angular velocity of 1800 rotations per minute in a magnetic field of flux density 0.365 Tesla. So calculate the induced EMF or electromotive force in the coil if it rotates a quarter rotation from zero position.
Firstly, as we said before, taking the givens from the problem, return the words to numbers and identify the right relation which can we use to solve the problem. Let us see how we can solve this problem. Firstly, you have number of turns per minute. Number of turns per minute. So, if we say the frequency equals number of turns per 60 seconds, we can conclude frequency equals 1800 divided 60 equals finally 30 Hertz. What is the benefit from the using frequency? Because frequency will determine the periodic time. Tau equal the inverse of frequency. Tau equal 1 divided nu equals finally 1 divided 30. But we're talking about quarter cycle or quarter rotation. So T equals quarter tau. Finally, time taken equals 1 divided 120 seconds. Since delta phi m equals A times delta B, therefore A 25 times 15 times 10 power negative 4. Why? Because 25 is centimeter, 15 centimeter. So we must convert them into meter. How? The area when it is written was centimeter square converted into meter square by times 10 power of negative 4. All of this part indicates the area of the coil. Then delta B, the change in magnetic flux, 0.365 equals finally the result in Weber, because the magnetic flux is calculated with Weber. Since EMF induced equal negative N delta phi m divided delta T as Faraday explained, so we will write the number of turns 30. Delta phi m we calculate before equals the result, divide delta T for what? Quarter rotation, so 1 divided 120. Finally, the induced EMF equals 49.275 volt. So, firstly, we must know that when the problem talks about number of rotation per time, that indicates what? Indicates the frequency. And we can use frequency to determine the periodic time. And then how much or what is the time taken in the rotation of the coil determine how many times of the periodic time, half, quarter, third, and so on. But firstly, we must to determine the frequency and then periodic time to determine the time of rotation. Let us see another problem with Mr. Racer.
All right, we are moving to another problem. This one says the magnetic flux changes in a coil of 500 turns through time according to the following figure, and we have this figure shown on the screen, and it says calculate the induced EMF or electromotive force in 3 stages.
Firstly, we must notice that the magnetic flux changes from A to B, then from P to C, and finally from C to D. There indicates the x-axis indicates the time of changes. So from A to B, delta phi m was 0.03 minus 0. And the time taken, 0.1. From P to C, the change of magnetic flux equals 0 because there is no change. 0.03 minus 0.03, so the result equals 0. Through time, 0.2 second. Finally, from C to D, the magnetic flux changed from 0.03 into 0, vanished. Through from 0.3 to 0.5, so we have 0.2 seconds. Let us see how we can calculate it. Firstly, from A to B, induced electromotive force equals negative N delta phi M divided delta T, equals the number of turns is given as 500. The change of flux from A to B equals from 0 to 0.03 equals 0.03. Divide delta T, the time taken, 0.1. Finally, we can calculate it, so the induced electromotive force equal 150 volts. From B to C, the induced EMF equals negative N delta phi M divided delta T. The number of turns 500. The change in flux, magnetic flux, equals 0.03 minus 0.03 equals finally 0. Divide delta T 0.2 from 0.1 to 0.3, so delta T equals 0.2 equal finally 0. In the same step, we can calculate the induced electromotive force from C to D as EMF equals negative N delta phi M divide delta T. Number of turns 500. Delta phi M equals, it is changed from 0.03 to 0. So 0 minus 0.03 equal negative 0.03 equals negative 0.03, but we have negative sign in front of the number of turns, so finally it will be 0.03. Divide time from 0.3 into 0.5, so we have the time of change 0.2. Finally, the answer will be EMF equals 75 volts.
Okay, now
let us see another problem with Mr. Yes.
All right. This problem says a solenoid of 1000 turns of resistance 70 ohm is wound around a wooden cylinder of diameter 7 centimeters and put in a magnetic field of flux density 2 Tesla, which was parallel to the axis of the cylinder. If it is stepped down to